In the course of time, many varied methods of transmitting sound signals have been evolved. And now it is even possible to transmit moving pictures, television pictures. You will no doubt know that with television, the impression of motion is simulated by a very rapid succession of individually constructed pictures. The camera sees each scene as a microscopic mosaic of bright and dark spots. These spots are scanned by an electron beam and analyzed line by line. The brightness information obtained from each spot is transmitted to the receivers, where the scene is reconstructed. Once the first picture is complete, others are transmitted in quick succession, so that the impression of a moving picture is obtained. In this film, the working principles of a modern camera tube are explained. It is known as the Vidicon, or, when constructed with a different photosensitive material, the Plumicon. The various parts of this camera tube are contained within an evacuated glass envelope of between 10 to 20 centimeters in length. At the front of the tube is a photosensitive signal plate, onto which the image to be transmitted is projected. For simplicity, we will show it the right way up. Situated at the other end is the electron gun, which directs an electron beam towards the signal plate. Around the tube is a focusing coil and two deflection coils which cause the electron beam to scan the signal plate. The signal plate then transforms the incident light into a picture signal that can be fed to the transmitter. Now that we've discussed briefly the construction of the tube, we will examine the various parts individually. To begin with, the electron gun. A metal plate, the cathode, is positioned in the vacuum tube and heated by a filament. Due to this heating, many free-moving electrons are released from the surface of the plate. By chemically coating the surface, electron emission increases and a cloud of electrons forms around the cathode. Electrons are negatively charged. Therefore, another plate, the anode, is placed in front of it and made positive by means of a battery. The negative electrons are then attracted by the positive anode. They then flow from the anode to the positive pole of the battery, are returned to the cathode, and are again emitted. Thus, the cathode produces a continuous flow of electrons. Positioned between the cathode and anode is a Waynoldt cylinder, which enables the flow of electrons to be controlled. When the negative charge applied to the Waynoldt cylinder is increased, the cathode will emit fewer electrons. The speed of these electrons in the direction of the anode is, of course, very high, and by making a small aperture in the anode, a number of these electrons will be shot through it. In this way, an electron beam is produced, which is used to scan the signal plate. The electron beam is surrounded by a cylindrical electrode having, at the right, a fine metal mesh, and at the left, an electrical connection with the anode. As anode, cylinder, and mesh have the same potential, the velocity of the beam will not be affected. The tube will only function properly if the correct voltages are applied. The cathode may be at 0 volts, the Weynoldt cylinder at a low negative voltage, and the anode, including the cylinder and mesh, at a relatively high positive voltage. In contrast to the anode system, the voltage applied to the signal plate is low, and this causes the electrons to decelerate and to strike the plate with a very low velocity. For practical reasons, the shape of the electrode system is somewhat modified. Although the electron beam is principally a thin, parallel stream of electrons, some spreading does in fact occur. Consequently, it is too wide to satisfactorily scan the small picture details, but it can be focused by a magnetic field. Consider a magnetic field, and in it a copper wire through which a current flows. A force is exerted on the electrons, and the conductor is caused to move. This so-called Lorentz force is exerted on any electron that moves in a magnetic field, including one emitted by an electron gun. Without this field, it would continue in the same direction. But with a magnetic field, the Lorentz force deflects the electron upwards. The strength of the field can be increased to such an extent that the electron is forced into a circular path. The same force is exerted on electrons which move at an angle to the right. Here, the circular motion is combined with the initial movement to the right, resulting in a helical trajectory. In the camera tube, the gun is positioned along the axis of the magnetic field, and you will see that some of the electrons travel parallel to the lines of force. Other electrons will spread out and move along a helical path, passing through the axis of the field on completion of each loop. The velocity of the electrons is such that they all pass through the same point on the axis. Thus, the beam is focused. The stronger the magnetic field, the stronger will be the focusing effect. But for optimum focusing, the field strength should be such that the focal point occurs exactly at the signal plate, and this is achieved by controlling the current flowing in the focusing coil. Another coil assembly comprising deflection coils provides the scanning motion. If we first consider the coils shown here and apply a direct current to them, a magnetic field will be produced which deflects the electron beam to one side. If the direction of the current is then reversed, the beam will be deflected to the other side, and an alternating current will cause a rhythmic movement of the beam. In practice, a sawtooth current is applied. The beam then moves slowly to one side and returns quickly to the other. However, in order to scan the whole picture, we require not only horizontal deflection, but also vertical deflection. And to achieve this, a second set of coils is necessary. The magnetic field set up by these coils gives the electron beam a vertical movement, and by combining this horizontal and vertical deflection, the complete picture is scanned, 25 times per second. But what is the effect of this scanning process on the signal plate? And how is the picture signal obtained? As we have already seen, the signal plate is situated at the front of the camera tube. First, the inside face of the glass tube is coated with a thin film of tin oxide. This layer is so thin that light will pass through it. Moreover, tin oxide is a good electrical conductor containing many free electrons. A second layer, this time of a photoconductive material, is applied. In the Vidicon, this is usually of antimony trisulfide, whereas in the Plumbicon, it is of lead monoxide. The electron beam is directed towards the photoconductive layer. The transparent conducting film through which the light passes is connected to the positive pole of a battery. Let us first consider what happens when no light falls on the signal plate. The electron beam starts to scan the signal plate. In the dark, a photoconductor has a very high resistance, and therefore the electrons will not pass through it. The negative charge possessed by these electrons will repel the similarly charged electrons in the transparent film back to the battery. This action occurs over the complete area of the signal plate, leaving the film positively charged. We will show this a second time. "25 times per second, the electron beam scans the plate. But the negative charge repels the new stream of electrons, and these are then collected by the electrode system. This non-conducting signal plate behaves in a similar way to a charged capacitor. That is, it may be considered to comprise a number of extremely small capacitors. At the left, each capacitor has an excess of negatively charged electrons, and at the right, a shortage of electrons, making it positive. In between is the photoconductive layer, which is, like any material, composed of atoms. The nuclei are shown in red, and the electrons in orbit around them in green. The photoconductivity is due to the electrons in the outer shell. These electrons are exposed to two forces. Firstly, the attraction of the positive nucleus, which binds the electrons to the atom, and secondly, the force exerted by the electric charge of the signal plate. The negative charge at the left and the positive at the right. The electric field created between these two charges exerts a force on the electrons, directed to the right. Consequently, all the electrons of the atom will move slightly to the right, but they will not break away from the nucleus. However, the situation changes considerably when light shines upon the signal plate. Light can be considered as a flow of energy quantums or photons. They penetrate the tin oxide and are absorbed by the photoconductive layer, just like the photon you now see passing the nucleus. Its energy sets free an electron which now moves to the positive layer. The following photons produce a similar effect. The vacancies left by the moving electrons are in turn occupied by electrons from neighboring atoms. This can be clearly seen from the diagram of one of the small charged capacitors. The last vacancy will be occupied by an electron deposited earlier by the electron beam. The electron deficiency at the left is regularly replenished by the passing electron beam. Simultaneously at the right, an equal number of electrons are returned to the battery. Poor light produces only a weak charge current, as can be seen from the meter. But as the light increases, the current becomes correspondingly stronger. In this way, the intensity of the light is translated into small current pulses, not only within these small capacitors, but throughout the signal plate. As we've seen, the scanning process divides the picture into a large number of horizontal lines. Let us then consider what happens in the signal plate along one of these lines. When the tube is switched on, the signal plate becomes charged. The light of the scene sets off the photoconduction process and discharge occurs. Where strong light is present, a large discharge takes place. But wherever the light intensity is less, a correspondingly lower discharge occurs. In this way, all the light impressions are stored and then transformed by the electron beam into charge impulses. This scanning process goes on repeatedly, line after line and picture after picture, producing an uninterrupted series of charge impulses which, due to their amplitude differences, carry all the picture information. The television picture signal formed in this way is sent out by the transmitter, detected by the receivers, and finally converted into a luminous, live television picture.